Alright, this is chapter 15 homework. I'm just going to start with the very end with problem number 10. So we have a disk that is on a rotating spindle here, and we have our coordinate system set up, which actually I went ahead and changed it down here. I'm going to start down here actually, kind of refer to up here. We have our major axes, the capital X, capital Z, capital Y. And the disk is rotating on the I axis with omega 1, and then the disk itself is rotating on the K axis with W2, which I had identified up here. And then we're going to lay out our initial conditions. Our radius is 3 inches, our omega 2 is 4 radians per second, and omega 1 is 5 radians per second, and the current angle is 30 degrees. So we are supposed to find our acceleration of point P, so we're going to start out with our acceleration of P equals AP prime plus AP in regards to F, which the F frame is the smaller frame of, or is the F frame is the smaller frame of reference, the lowercase x, lowercase y, lowercase z. And then we have our AP prime is omega crossed with omega cross r. Omega is capital Omega is omega 1 I hat, which is 5 radians per second. We'll go ahead and cross the I'll go ahead and cross the we'll go ahead and cross the conditions here, and then it will come out to be 5 radians per second. I hat crossed with 2.5 inches per second K hat. That's to get the AP prime, because the omega crossed with R, yeah, that's what that was. So so we have our R condition, which is the 3 cosine 30, 3 cosine 30. Yeah, anyway, that's how we got to that part. Anyway, our acceleration of P in regards to frame F is omega 2 crossed with omega 2 crossed R, which eventually comes out to be AP acceleration of P in regards to F is 41.6 inches per second squared I hat plus 24 inches per second squared J hat, and then our Coriolis acceleration is 2 omega crossed with velocity of P in regards to F, which after doing all of our crossing and everything comes out to be 20.4 K hat. And then we'll go ahead and take the Coriolis acceleration, the star there, the acceleration of P in regards to the frame starred there, and our AP prime starred there, and go ahead and plug those into our AP equation, and our final answer is acceleration of the point is equal to 41.6 inches per second squared I hat plus 36.5 inches per second squared J hat plus 20.4 inches per second squared K hat. Question number 9. Question number 9, we have 2 rods connected by a collar, rod A, P. Collar is P, connect to rod BD. First off, we will set our coordinate system. Y is up, X is to the right, and the positive moment is counterclockwise. Our initial conditions are the angular velocity of AP is 5 radians per second in the positive sense, and the angular acceleration of AP is equal to 2 radians per second squared in the negative sense, the clockwise direction. I just didn't put the negative there because I already put the clockwise swirly. And then just to get some additional information that we're going to use later, we went ahead and figured out our angles. So beta is 45 degrees. Our and then we did our law of sines so that we could get the distances of F, the length of rod AP, and the length of rod BD from B to P, which is E. And then F is 265.79 millimeters, E is 119.53 millimeters. I'll come back to that in a minute. The velocity is equal to omega r, the angular velocity r, and then our velocity of p is our 5 radians per second. So we'll go ahead and set that up because we want to find the velocity of p, and then eventually convert that in. We want to find the velocity of p in regards to AP, and then figure out the angular velocity. We want to find the tangential velocity of p in regards to A, and then we want to turn that into a tangential velocity of p in regards to BD. So we get our and by the way, we were trying to find our angular velocity of BD and our angular acceleration of BD as well. So our velocity in regards to our velocity of p, which is in regards to A, is 1328.93 millimeters per second in 25 degrees northwest. And then we'll do a little bit of geometry here and figure out that the velocity of p in regards to A is 45 degrees off of velocity of p in regards to BD. So then we will stick that into our cosine equation. So we'll get our velocity of p in regards to BD is 939.70 millimeters per second. We then use that velocity with a radius which is equal to b, the distance between B and P, which we denoted as E, and that gives us the angular velocity of BD equals 7.8613 radians per second. Then to find our angular acceleration of BD, go ahead and split up our I guess I didn't end up needing to use the normal acceleration, but so I just used the tangential acceleration. Basically did the same thing that I did with the tangential velocity, where I went ahead and found the tangential acceleration is 531.58 millimeters per second squared, 25 degrees in the southeast direction, which which then gave me an acceleration, the tangential acceleration of p in the BD, tangential to the BD line of 375.88 millimeters per second squared, and plug that into our tangential acceleration equals radius times angular acceleration, which gives us angular acceleration equals 3.1447 radians per second squared. And then question number 8. We have a disc that is 5 inches in diameter total, attached to a smaller disc of 3 inches. We have our points A, B, and C, which are desired, which are what we're looking for. The velocity, the initial velocity the velocity at the moment, at this instant, is 8 inches per second to the left. And I'm sorry, that's the velocity of D. So we're saying these in regards to the rope D pulling to the left, and then the acceleration of D is also going to the left with 30 inches per second. So we need to find the acceleration of A, acceleration of B, and acceleration of C, tangential. Acceleration equals radius times angular acceleration, which gives us our negative 30 inches per second squared equals 5 inches angular acceleration, which gives us our negative 6 radians per second squared, which means that it's going in that the whole disk is going in the clockwise direction, or it's accelerating in the clockwise direction. And then velocity equals radius times omega is -8 inches per second equals 5 inches times omega, which equals, or angular acceleration omega equals -1.6 radians per second. I went and starred those because we're going to be using them later. And then and then we went ahead and wrote out our acceleration formula. AB equals our acceleration of b equals the acceleration of g plus acceleration of b in regards to g. And we'll be using those for A, B, and C. I just picked B for now. And we can split a acceleration of b in regards to g into our normal and tangential accelerations, which then convert over to our acceleration of b equals acceleration of g plus angular acceleration times the radius of b in regards to g minus the angular velocity omega squared crossed with RBG, which we got that from our picture equation, which you have all of the accelerations in the translating. All of the accelerations are translating to the right, and then we also have our rotation acceleration if g is fixed, which gives us C, A, and B all having normal and tangential accelerations, and then that eventually all cancels out so that C has a tangential acceleration, A has a normal acceleration, and B has a normal acceleration. So first we needed to find out what is the acceleration of g. So we went ahead and set up a little picture here with A is fixed, the acceleration of g is 3 inches away, and the acceleration of B tangential is 2 inches, which the acceleration of B tangential is the same as acceleration of d, and the acceleration is equal to the radius times angular acceleration, which gives us our angular acceleration is 15 radians per second squared. Acceleration of g is 3 inches away from that, so our acceleration of g is 45 inches per second squared. So then we wrote up our equation, got everything set up. Back down here, the equation we had set up here, which is the ag plus alpha rbg minus omega squared rbg, so which gives us our acceleration of b equals 45 inches per second squared, or per second squared in the I direction, plus -6 radians per second squared times 5 inches in the j direction, minus 1.6 millimeters per second, and then we're going to square that times 5 inches in the j direction. And then I didn't get any further than that, but there's our chapter 15 homework.